Hi, I'm Dan Gibney, and today I will be discussing with you recent results by Chirag Jain, Sharma Thenkachan, and me on the problem of collinear chaining. Let's start with motivating and describing collinear chaining. As everyone watching this probably knows, sequence alignment is one of the most fundamental problems in computational biology. Unfortunately, computing an optimal sequence alignment is not as easy as we might like. Even when we look at only two sequences, doing significantly better than the quadratic time dynamic programming algorithm for edit distance seems hard. This is something that has been shown through conditional lower bounds based on the strong exponential time hypothesis. So we turn to heuristics, which is where collinear chaining comes in. In the version of collinear chaining we will consider here, we start with a pre-computed collection of exact matches called anchors. Our aim is to find a collection of anchors that we wish to keep. Then these anchors can be used as a sort of coarse-grained sequence alignment. Then later this coarse-grained sequence alignment can be further extended as needed using seed extension heuristics. So here's an illustration of a collection of anchors representing exact matches, shown as rectangles. Now the aim is to find an optimal subset of these anchors subject to some cost function. And one possible example is given here with these two anchors. Techniques like this are used for long-read mappers like minimap2, minigraph, or winnowmap2, and also for genetic alignment tools like Nusimer, Clasp, and Coconut. There are different algorithms for this problem that depend on the cost function that we're working with. For cost functions where the overlap is not allowed, where there's no overlap allowed between anchors, there exists an algorithm running in time big O n log n log n time. For cost functions where overlap between anchors is allowed, but the gap between anchors is not considered in the cost function, there exists an algorithm running in time big O n log squared n. Now, prior to our work, there was no algorithm for both overlap and gap, cost being allowed in the function, the cost function. And that's a problem because arguably having both is a more realistic model. There's no reason to assume that in an optimal alignment, the anchors would be non-overlapping. And also not taking into account large gaps between the anchors seems unlikely to produce something close to an optimal alignment. So to address this issue, let's discuss the cost function which we can use that accounts for both of these. We'll start with a bit of notation here. Each anchor has 4 associated values. 2 are for the first string and 2 are for the second. For an anchor I, we'll use IA and IB to denote the 2 values for the first string, and IC and ID the 2 values for the second string. With these 2 values, or with these 4 values, we can define a partial ordering or precedence between the anchors. We say an anchor I dash is less than I under weak precedence if I dash dot A is less or equal to I dot A, and I dash dot C is less or equal to I dot C. We say an anchor I dash is less than I under strong precedence if I dash dot A is less or equal to I dot A, I dash dot B is less or equal to I dot B, I dash dot C is less or equal to I dot C, and I dash D is less or equal to I dot D. Now with that, we can discuss the cost for an ordered set of anchors. The gap cost between anchor I dash and I is going to be the larger of the 2 gaps occurring between the 2 anchors, written formally here in this first line. The overlap cost between anchor I dash and I is going to be the absolute difference in overlap between the 2 anchors, written here in the second part. And the cost of the ordered set of anchors is going to be defined as the sum of the gap and overlap costs taken between adjacent anchors in the ordered sequence. Now, let's look at what we were able to do using this cost function. So we can provide an algorithm that solves the collinear chaining problem with overlapping gap costs in time big O tilde n. Here, this big O tilde n hides polylogarithmic factors. And here are some special cases where we can actually give the logarithmic factors. For chains with fixed length anchors, we can solve this problem in big O n log squared n time. For chains under weak precedence, not necessarily fixed length anchors, we can solve the problem in big O n log cubed n time. And for chains under strict precedence, we can solve the problem in big O n log to the 4n time. Of course, this is just the overall result. There's not enough time in this presentation to go into all the technical details of the algorithm. It involves the analysis of several different cases and the use of dynamic range minimum query data structures in order to avoid checking all sorts of anchors in order to find the optimal one at every step. If you're interested in that, there's way more technical details in the paper, and I suggest you check it out. Okay, our second main result is proving the equivalence between collinear chaining under the cost function that we use and a generalized form of edit distance we call anchored edit distance. In this generalized version of edit distance, we have that exact matches that are not supported by an anchor will incur a unit cost. Now, this results in the dynamic programming solution written here. The only difference between this and the usual edit distance dynamic programming is that the x variable written here is 0 only when both an exact match occurs and that match is supported by an anchor. This illustration of an alignment shows exact matches as solid edges, substitutions as dotted edges, and deletions as x's. And the key here is that any solid edge is always going to be supported by an anchor in anchored edit distance. Now, our work proves the following equivalences. For a fixed set of anchors, the following quantities are equal: the optimal anchored edit distance, the optimal collinear chaining cost under strict precedence, and the optimal collinear chaining cost under weak precedence. This makes the first direct theoretical connection that we're aware of between collinear chaining and edit distance. The proof of equivalence consists of two main parts. The first part is showing that given a set of anchors, we can obtain an alignment with the same edit cost. This is not that difficult. In fact, many of the considerations that motivated our definition of the cost function were based on this. The cost function for collinear chaining we developed takes into account the needed deletions between two anchors in terms of gap cost. The cost function also takes into account the needed substitutions for two anchors to overlapping anchors in terms of the overlap cost. The more difficult part is going the other way. In this other direction, we start with an optimal alignment under some set of anchors and have to come up with a subset of these anchors. This subset should have the property that its collinear chaining cost is equal to the anchored edit cost that we started with. To do this requires a number of steps, including eliminating extra or nested anchors until we obtain an ordered subset. In our proof, we convert the starting set of anchors into a strictly ordered subset with the desired property. This is the trickiest part and involves some arguments about how anchors can be removed while maintaining an alignment with the same score. After all of this is done, we show that on this subset of anchors, the collinear chaining cost is equal to the alignment cost. Now, I'd like to briefly discuss some experiments we did based on our results, and I'm going to start with the implementation. The pseudocode for our implementation is shown here on the left. To compute the optimal collinear chaining cost, we used an approach that guesses the optimal solution value. We then use that guess to bound the number of anchors that have to be considered at every step. The algorithm then increases that guess by a constant factor, does this every iteration until no better solution is found. And we are able to show using this algorithm that it runs in average case time, big O n times opt plus n log n, over all possible inputs where the number of anchors is less than the longer sequence length. This is a property that always holds true for maximum unique matches, or MUMs. Finally, let's look at some experimental results. The tool we implemented is called ChainX. In this chart, we see that, like these other tools, ChainX is more time and space efficient than edlib, which is computing the actual edit distance. The time is comparable to these other tools. Now, to look at its performance, we use the absolute value of the Pearson coefficient, and we look at that lets us look at the correlation between the chaining scores and the edit distance. And what we can see is that our implementation achieves a high Pearson correlation across a wider range of similarities, or similarity range. That is, across a wider range of mutation rates when applied to the target string. Now, looking at ChainX for phylogenetic tree construction, we can see that the family of genomes, on the family of genomes that we tested it on, ChainX produces a tree with an identical structure as edlib. This was a family of E. coli genomes that was created using the same simulation methodology as Marquis et al. And overall, this experiment demonstrates that ChainX's strong correlation with edit distance makes it useful for recovering the history of insertion events. All right, this concludes my talk. I hope it was informative. If you're interested, I encourage you to look at our work entitled Collinear Chaining with Overlaps and Gap Costs. Thank you for your time.